Again, your final exam will be Tuesday from 9 to 11. Does that sound right to everyone?
Yeah.
Yep. And I can write it on here. Final Tuesday, 9 to 11. And you know, it's going to be on those last couple of chapters that we've covered and some of the information that's going to be on it. If I start hitting these highlights, you should be nodding your head, okay, okay, okay. So I'm going to talk about what's going to be on the final, and then we'll go back to a little bit of what we did last Thursday, and then we'll finish up. As I said, we've done a good job this semester staying on schedule. We haven't missed any snow days or anything like that. So we got all of our material in. The sorting we talked about, we had the three main categories: the selection, the exchange, and the insertion. Okay, again, the selection was I went through and found an item and then I swapped it around. The exchange is when I looked at side-by-side pairs, and the insertion, which one was the bubble sort?
Exchange.
Yeah, it was a type of exchange sort. We did we did a couple down here below that you're going to see. The quick sort. Which one was the quick sort? What would that fall into? Well, what was the quick sort? Quick sort was I took the first number and called it my pivot, and then I went through and I put numbers lower than the pivot on the left side next to it and numbers higher than the pivot on the right side, and then switched the middle and the pivot. So I'm thinking that would be some sort of exchange, because as we went through, we were exchanging numbers. Okay, so we had a bunch from 161 up here. The insertion sort. What do you think of when I say the insertion sort?
So divide into left and right based on insertion.
No, sounds like facilities here. That's good to know. Insertion sort. This was cards. If I was playing cards and I'm picking cards up in my hand, if I pick up a 5, I put it in my hand. If I pick up a 3, I insert it to the left of the 5. If I pick up a 9, I go through, and so as I input the numbers, I'm inserting them right into the correct spot. And that was, in fact, the type of sorting. We didn't do a lot with that. All right, when I say heap, you say heapify. Sound about right? And what did I know about a heap? A heap was complete. That means it was filled in from top to bottom, left to right. And what was the other rule for a heap? Every
parent must be larger.
Right, every parent must be larger than its children. And, when I got ready to sort, I took the top number of the heap, moved it to the end, and moved the bottom one up. And then I did a, what was that called?
Percolating.
Yeah, I percolated down. So I had to percolate up. I had to percolate down. We looked at merge sort. Okay, the merge sort, we looked at two different ones. Binary, that occurred when I had a power of 2 number of elements, or the natural. And we had runs for both of those. And if you forget, there are videos to go back and take a look at it. Huffman Codes, another type of working with binary tree, was the Huffman Codes, and that was for decodability. I could do the 0, 1, 1, 0, 1, 0, and if you had the key, you could quickly figure out. So chances are on the final, I'm going to give you some letters and some percentages and ask you to build a Huffman code so something could be quickly codable and decodable. We got into trees. We had the Adelson-Velsky-Landis rotate left, rotate right, rotate left, right, rotate right, left. Did a bunch with that. We had the 2, 3, 4 trees. They were the ones that had 4 pointers and 3 storage spots. And we looked at, when we filled it, we split it and broke it down. If it was at the parent, at the root. If it was one of the children, we split it and tried to move it up. We had B trees or M trees, M node trees, where, you know, we looked at that one chart. What if I had 10 things inside of my node and 11 pointers to go with it, kind of deal. And then we talked about red black. And in order to do the red black, we sort of had to understand the 2, 3, 4. And red meant, if I had a red line, it meant it was a sibling. If it was a black line, it was a parent-child relationship. Going again back to the 2, 3, 4. The digraphs, we got into the digraphs. We talked about these have a direction. We were looking at vertices and nodes, or we were looking at directed arcs, you know, to connect them. And we're going to jump back into one of those in a few minutes. And then finally, for the final, I told you, you know, if I say, give you Adelson-Velsky, you know, it was a way of balancing a tree that was Adelson-Velsky-Landis. If I asked you the one for today. So there's about 5 or 6 names you should go back through the book and take a look at. The one we're going to talk about today, a guy named Dijkstra is famous for, and that's the shortest path algorithm. But in order to deal with the shortest path algorithm, we're going to start with the tree that you see, or the graph, excuse me, not a tree. It's a graph. It's a directed graph. We have vertices. We have directed arcs. And if I said I'd like to do a breadth search and I want to start at A, where would I go next? Well, I have choices. I actually have 3 choices, but you're probably going to tell me where to go. Now, again, breadth is go wide, not deep. In a minute, we'll take a look at the other one, which is the depth. But for now, we're going to do breadth and start talking. A goes to
B, D,
B, D, and E. So again, I'm going to take care of A, and now I'm going to go to B, D, and E. And we talked about this the other day. When I do the breadth and I take a look at what's here, I know this group is all one trip away, one arc away. You can also follow along with this in the NIOF book on page 899, and we're actually going to go there in a minute. But for now, let's keep going. So I took care of the A, and everybody connected to who A was. Now I'm going to move over to the B. And who does the B connect to that hasn't already been connected? B goes to just
F,
F. Okay. Who does D go to?
C, and H.
C and H. And who does D go to? That's who we just took care of. Correct?
E goes to nothing.
Okay, hold on a
H,
second.
B.
A goes to B, D, and E. And we said we're going to distinguish that this way. Now we have B. B goes to F. We're okay with that. D goes to C and H. We're okay with D. And E goes to just H.
Which is G.
So at this point, if you remember, I said if I wanted to go to any of these locations, F, C, or H, these are now sort of categorized as being 2 trips away. Okay. Starting at F, where can I go that hasn't already been gone to?
G and
I.
I.
G and I. Okay. Took care of F. C, where can it go that hasn't already been gone to?
Nowhere.
Nowhere.
Or,
And H. H can't go anywhere. Okay, now I move to my next group, G. G can go to nowhere new, and I can go to nowhere new. And one of the things we said, if we were actually coding this, we'd also want to know how many nodes there are, because I might be keeping a count, and all of a sudden I say, oh, I actually reached them all. I wouldn't have to check anymore. But again, A, all of these are 1 stop away. These are 2 stops away. And G and I, if I start at A, I can get to in 3 moves. And again, if I pick G, I can go 1, 2, 3 to B to F to G. So that was an example of breadth. Now let's see if we can do an example of depth. Starting at A, let's go with A again. Give me a run from A.
A to B to F to I to
A to
H
B to F to I
to
to
H.
H. Okay. Now, where did I go after I stopped at H?
You start with the B
No,
or
that was the breadth.
the A B A D.
Nope. Well, I remember this one, I went and backtracked. So I was at H, now I
Oh,
backtracked to I. Can I go anywhere else? No. Backtrack to F. Can F go anywhere else?
G,
Yes.
Yeah, to G, to
C,
to
C.
C, to
D,
D.
Delta.
but
H.
isn't this the method where you ask where they want to start, sort of thing, or?
Right, right. We're just starting at A. But remember, the depth was I went as far as I could, and then I backtracked and kept seeing if I could go any farther. And, you know, if you remember, we first looked at this as a binary one. And we started here, and we went down, and then we backtracked and to see if we can go down. We can, and then we backtracked and went down, and then we kept going down, and then backtrack, and finally we were done. So it was one of those where I kept going back. So I can go, and now I might want to be doing something like A to B to F to I. You said to H, and I stopped. So I'm going back to I. I can't go anywhere. I go back to F, which says I can go to G. I can go to C. I can go to D. D goes to H, but I've already been there. So D's done. I go back. Can C go anywhere else? No. Can G go anywhere else? No. And now, you know, I keep going all the way back. I already am here to F, to B, to A. Can A go anywhere else? Well, it says D,
Echo.
but we've been there. And then finally, my last stop would in fact be at E. Okay. And again, I might want to have some sort of count going on so that I know that I hit them all. So that was the depth search. Okay. Questions? Now, if you jump in your book, and you don't have to because I actually printed the page out to make this a little bit easier. You see a chart that looks like this, and that's the picture I just had. And we did the search, and as we went through, we said A goes to B, D, and E. A went to B, D, and E, and that was that first group we had. So A to A, you know, we don't need to worry about A to A, but there was one path to B, one to E, or excuse me, one to D, and one to E. It's one path away. Now I take a look at B. B can go to, looks like I'm going to add just F to it. So now FB, this guy becomes a 2. Let's see what else can be. If I go to D, C and H can be added to it. So there's a 2 and there's a 2. What I'm going to end up with here, and again, this is page 899 in the book, I'm going to end up with a chart of starting at A, how far away are these? So not only am I doing this list like we did horizontally instead of vertically, I'm actually coming up with a number scheme. Now, I know you can't see it, but it's in the book, and I want you to tell me where the error is. In this table in the book, there's an error. Yeah, again, I apologize. You can't see this so well. But some of those numbers are small. So, you know, I'm looking at this. A goes to B, D, and E. And these are all level 1s. Now I'm taking a look at B. The only thing new I'm adding is F. So that becomes a level 2. I'm looking at D. D is going to add C and H. So they each become 2s. And E, which was my third one up here, added nothing.
Hmm.
So I stay with this new line, okay? So this first calculation did all of my ones. Second group did my twos. So I did A, it connected to B, D, and E. Here's B, D, and E. Created from B, D, and E were F, C, and H. So now F is a distance of 2. F connects to, let's see, what's new? G and I. So G becomes a 3, and I becomes a 3. Well, here's where the mistake is. For some reason in his chart, he changes those to 2s, and they should still be 1s. Because to get from A to this column, which is E, it's always going to be 1 pass away. So I kind of gave you the answer as we worked through it. But first time I saw this in the book years ago, I'm like, come on, man, I think you messed something up. And these are supposed to be 1s. So starting at A, now that this chart is done, I can get to B in 1 pass. I can get to C in 2, D in 1. These should be 1s, 2s, 3s, 2s, and 3s. Which again, that's similar to what we talked about up here when we were doing 1s, 2s, and 3s. Any questions? Any comments? All right. What I want you to do now is I want you to go to D2L. There should be a HTML file for chapter 16 from the NIOF book. And in there, I want you to load up a program called The Shortest Distance and load that into, you're going to have to copy and paste, load it into C++, and we're going to see if we can get it up and running. Now, you're going to need a data file that goes with it. And the data file is in the book on page 907. Okay? Page 907. So I'm going to pause the video while you folks go and load that up. So let's take a look at the data file. The first item in the data file is LA 3346. So it's probably important to understand what's going on. LA is now numbered city number 1. Okay, and as we go through the data file, number 2 becomes San Francisco, 3 is Denver, 4 is Chicago, 5 Boston, 6 New York, 7 Miami, and 8 New Orleans. And each one of them starts with a number. For example, in LA, it starts with 3, followed by 3, 4, and 6. And what that's telling us is LA connects to 3 cities. It connects to number 3, which is Denver, number 4, which is to Chicago, and number 6, which is New York. San Francisco is at 3 cities. It connects to number 1, which is LA. It connects to number 3, which is Denver, and it connects to number 4, which again is Chicago. So taking a look at what this data looks like, we use a picture to get a feel for what's going on. Denver connects to 3 cities. Denver connects to number 1, which is LA. Denver connects to itself. And finally, Denver connects to number 2, which is San Francisco. Number 4 is Chicago. It only connects to 2 cities. It connects to number 3, which is Denver. And it connects to number 8, which is New Orleans. Boston connects to number 4, which is Chicago, and number 6, which is New York. New York connects to 4, which is Chicago, 7, which is Miami, and 8, which is New Orleans. And finally, New Orleans connects to, Miami connects to 8, 3, and 5. Miami connects to 8, which is New Orleans. It connects to 3, which is Denver. Denver looks like a real popular place. And it connects to 5, which is Boston. Now, finally, New Orleans connects to Miami, which is 7. and it connects to LA, which is 1. So the idea behind this program that you're copy and pasting is building is if I pick a city and somebody tell me what city to pick.
Chicago.
Chicago. Okay. And so when I run the program, I want to end up where? Let's say LA. This program should tell me what's the shortest way to get from city number 4, which is Chicago, to LA. And I think I see the shortest, Chicago to Denver, Denver to LA. So if you write the program, it should say that's the shortest way to connect here. And why? Because it takes Chicago and does a breadth search. It connects to Denver, it connects to New Orleans. Then I go Denver. Denver connects to LA, San Francisco in itself. New Orleans connects to LA as well. Oh, there's a second option of path length 2 to get there. You know, I could see longer ways to get there. Chicago to New Orleans, to Miami, to Denver, to LA. So there's a way of 4. So if I did the chart like we looked at in the textbook and I started Chicago, I could see how many ways there are and what the shortest path would be to get to each one of the cities. And that would all come from the breadth search. So if you put in Chicago for your input and you're traveling to LA, are you getting an answer of 2?
1 moment. Let's see.
Does it say Chicago and then a down arrow to Denver and then a down arrow to LA?
Number of start city. You started Denver, right?
We started at Chicago, which is 4,
Okay. 4.
and the destination city was LA, which is 1. And it
gives
should
me. But shortest path is Chicago to Denver to Los Angeles.
right. Now, could it have also given me Chicago to New Orleans to Los Angeles? Sure. It just finds the first one that pops up numerically. So Chicago, the 3 is going to give me the path before we would hit the 8 path. But there would be thus another way to do it. But this is the shortest path algorithm. It's actually has another name, the traveling salesman. You know, how if he starts to travel around, how can he visit the most places the quickest possible way? Questions? Foster, did you get it to run?
Yes, I did, except for whatever reason, my cin function, like for every time I make a program now, like because we have a name starts city cin and then number of destinations cin again, it
Yeah.
just like automatically quits whenever I put in first start city. But I got it to run. Like the program itself is fine.
Okay. All right. Dean did make a comment in there in the chat to help everyone out. Hopefully you all caught that. But yeah, I think this is kind of neat, the shortest path algorithm. Again, you see the amount of code that's in this program, and a lot of you are probably thinking, yeah, I'm glad I didn't have to code that. So any questions on depth and breadth? Adam, are you okay with it?
Yep.
Yep. And for you Philly fans, you see the name Dykstra. There was a player named Lenny Dykstra at some point, some time ago. Any questions on anything on the final exam between sorting? When the final exam is, Tuesday 9 to 11. Different types of sorting, heaps, the quick, the merge, doing Huffman codes, stuff with trees, stuff with digraphs, and again, names like Adelson Velsky Landis or Dykstra, or because there'll be some questions with that.
That's slightly unrelated. You said we're not having class on Thursday.
That is correct.